Welcome to the Deep Dive, where we transform your raw source material into clear, captivating insights. Today, we're plunging into the really fascinating world of foundation models and generative AI. Our mission for this deep dive is to unpack the core conceptual breakthroughs behind these powerful technologies. We're going to explore not just what they are, but how they learn and get their incredible abilities,
Yeah.
really revealing the algorithms and this surprisingly simple objectives that drive them.
Yeah, it's quite a journey. We're going from some really insightful philosophical ideas about how the world is structured all the way to the very practical methods computers use to learn from just massive amounts of data. You'll gain a wide understanding of the underlying principles, sort of cutting through some of the engineering specifics to focus on the truly innovative concepts, the ones that really changed everything.
Yeah. Okay, so let's unpack this then. In our last deep dive, we briefly touched on foundation models and generative AI and how they learn by observation, emphasizing that meaning is deeply contextual and relational. But looking at our sources, it begs the question, why did we even need new ways of learning in the first place? What was the big problem with older methods? What was holding things back?
Well, the traditional approach, something called supervised learning, it relied on humans meticulously labeling every single piece of data. Think of it like this. If you want a model to recognize a cat, you literally show it, I don't know, millions of pictures and tell it, this is a cat, this is a cat, this is not a cat.
Tedious.
Incredibly tedious.
Yeah.
And it just doesn't scale. You can't label the whole world. It also struggled to generalize well to new situations it hadn't seen explicitly labeled. And then there's reinforcement learning. Powerful, sure, but it's like throwing a baby into a complex world with zero prior knowledge. You'd make basically no progress, and as one of our sources put it rather bluntly, die way before you make any progress whatsoever. It's just too risky and slow if you don't have some kind of foundation, some world model to start with.
Okay, so if manually labeling everything is out and pure trial and error is too slow and dangerous, what was the breakthrough? What's the secret sauce that allowed AI to suddenly learn so much so fast?
The key breakthrough, the thing that really shifted the paradigm, is self-supervised learning. This allows models to learn from entirely unlabeled data. They don't need a human telling them what's what.
How does that work?
They just need data itself. The data, in a way, contains its own supervision.
That sounds almost magical. Can you give us an intuitive sense of how a computer supervises itself? How does it learn without labels?
Yeah, think about how you learned what a dog is. You probably didn't need someone to label every single dog you ever saw, right?
No, I guess not.
You observed dogs in different contexts. You saw them, heard them bark, saw how they moved. You correlated and contrasted them with other concepts, like cats, for example. You developed a very relational understanding of meaning. Self-supervised learning leverages this exact same principle. It learns relationships and patterns just by observing the data itself. It figures out the structure on its own.
And our source material suggests a lot of these conceptual breakthroughs, especially early on, started with language. It makes a compelling argument that language is somehow unique. Why is language so special here?
Indeed, language is, well, fundamentally man-made, isn't it? And it's not just a tool we use for communication. We actually think in terms of language.
Right, our internal monologue.
Exactly. It's an incredibly efficient, sort of universal medium for transporting complex ideas, for verifying them, for building shared understanding. This unique nature kind of hints at why large language models might lead to more human-like intelligence.
It's kind of hard to imagine now, but back in the early days of AI, and we're not talking that long ago, each language task, like translation or question answering or classifying sentiment, it required its own dedicated research team.
Oh, absolutely. Its own massive data set, a specialized model built just for that one thing.
Our sources describe it as spreading ourselves thin, a really fragmented approach.
And that challenge, that fragmentation, led to a really pivotal question in the field. What if, instead of tackling each language task separately, what if we could find a single objective in language, like a core principle that we could optimize for? The hope, the big bet really, was that optimizing for this one thing would lead to a general understanding of language, which could then solve all these different tasks as just downstream task applications of that core understanding.
So the goal shifted. It wasn't just about making a better translator, but about teaching the AI to genuinely understand language in a much more flexible, general way. How did they even begin to capture something as slippery as meaning?
Well, the initial idea was to have an AI model digest language and then represent its meaning in a useful, computable format. Typically, this meant what we call high-dimensional vectors. You can think of these as just long lists of numbers,
Okay.
like a unique numerical fingerprint or a really detailed profile for each piece of meaning. This allows computers to actually process and compare concepts in a very nuanced way.
So, for example, if you take words like cat, kitten, dog, and puppy, you're saying the computer could assign numbers to them.
Yes, assign numbers in such a way that it automatically grasps these relationships.
Like species, cat and kitten are numerically closer than they are to dog, and maybe also age, where kitten and puppy are closer than cat and dog.
Precisely. And what's really fascinating here, and kind of the core challenge, is that the meaning of a single word isn't fixed, is it? It's super contextual.
Right, the classic example.
The classic example, riverbank versus financial bank. The meaning depends entirely on the surrounding words. So the real challenge wasn't just mapping words, but mapping sequences of text to these vectors, capturing that context.
This concept, that meaning in language is defined by the company it keeps, it feels incredibly profound, almost self-referential. It implies we can learn meaning just by observing how words naturally appear together. So how did they turn that, well, philosophical idea into a concrete training method for a computer?
One surprisingly effective method that emerged is called masked language modeling, or MLM. It's quite clever, actually. You take a sentence, you randomly mask or just hide a word.
Like a blank space.
Yeah, exactly. And then you train the model to predict that missing word based only on its surroundings, looking at the words both before and after the blank.
Huh. Like playing Mad Libs with the AI. So if I give the model, I went to the beach bank for a swim, and it correctly predicts river, it gets the context because of swim. And if I say I went to the beach bank to deposit money, and it predicts financial, it grasps that context too. Wow, that sounds incredibly powerful for getting a really good feature representation of text, basically allowing the model to read between the lines.
Exactly. It learns nuanced meaning from context. And this concept led directly to what's called pre-training.
Mm.
You take a huge model and train it on vast amounts of text using these self-supervised tasks like MLM to get a general language understanding.
Okay.
Then, for specific tasks, say, classifying Amazon reviews as positive or negative, you fine-tune a smaller, more specialized model on top of these powerful general features learned during pre-training. It's a bit like observing someone expertly driving a car for hours, soaking in all the general nuances of driving.
Right, learning the basics.
Before you actually get behind the wheel yourself for a very specific route or task.
That makes perfect sense. Pre-train for general knowledge, fine-tune for specifics. But then a new question arises, doesn't it? If language itself is so flexible and powerful, why stick with outputting these high-dimensional numbers? Why not just have the model output, well, language directly?
Absolutely. And that was the next big leap, a real turning point. Instead of mapping text to numbers that then needed another layer of interpretation, models started going directly from text input to text output.
So much simpler.
Much simpler. It means tasks like sentiment analysis don't need to output a 0 or a 1. They can simply output the word positive or negative as text. This makes the whole engineering process much more unified across vastly different tasks. Everything becomes text in, text out.
Like a universal language interface for AI? I know Google's T5 model was a pioneer here, defining pretty much all NLP tasks as text-to-text. And instead of just predicting one masked word, it masked multiple words and had to predict the complete sentence with all those words filled in. But what about that other approach you mentioned, causal language modeling, or CLM? Our sources say there's a key difference there, too.
Right. This is an important distinction. What's the difference between masked language modeling, MLM, which we just discussed, and causal language modeling, CLM? MLM, remember, can look at words both before and after the masked word. It's bidirectional. This gives it more complete context and generally leads to a richer understanding of the input text.
Okay.
CLM, on the other hand, is unidirectional. It only looks at the previous words to predict the very next word in the sequence, like auto-completing text.
So CLM sounds more limited then, doesn't it? It only sees what came before.
In terms of pure understanding of a given text block, maybe?
But I also hear it's faster to train because it can be parallelized more easily.
That's true. The training can be more efficient. And here's where it gets really interesting. While MLM might be generally better for tasks requiring deep understanding of existing text, CLM is perfectly optimized for one very specific task, simply predicting the next word. And that single, seemingly incredibly simple task turns out to be astoundingly powerful when you scale it up The huge breakthrough behind models like ChatGPT was taking this simple concept of predicting the next token or word and just scaling it tremendously more data, bigger models, more computation. Suddenly, all those different tasks we talked about earlier, question answering, translation, summarization, even coding, they can all be effectively reframed as just text completion.
Wait, really? So you prompt it with something like, translate to German, my name is.
Exactly.
And the model's most logical, statistically probable completion, based on all the text it's seen, is the correct German translation.
That's the idea. Or you ask it a question, and the most probable sequence of words to follow that question is the answer.
That sounds crazy simple. But our sources indicate this was actually a huge bet by companies like OpenAI, spending hundreds of millions to see if scaling just this one ability
Just next word prediction.
could truly lead to human-level intelligence and all these surprising emergent abilities we see now.
And, well, it seems like the bet paid off.
It's incredible. Just predicting the next word, scaled up.
Wow. But these self-supervised principles, they aren't just limited to language, are they? You mentioned they apply elsewhere, like
Re-
images.
Absolutely. The underlying principles are quite universal. Take contrastive learning, for example. It's become very popular in computer vision. The core idea is brilliantly simple, really. It's based on the observation that, generally speaking, things that appear together in the same image are probably more related conceptually than things randomly picked from completely different images.
Okay, that makes intuitive sense. So how does that translate into training? You take an image, right? You take an image, and then you create two different sort of random crops or augmented views from that same image, think slightly different zooms or angles. And then you train the model to push their high-dimensional numerical representations, their fingerprints, closer together in its internal embedding space.
You're teaching it. These two views belong together. They mean something similar.
Exactly. But that alone isn't quite enough. If that's all you did, models could just learn one generic representation for everything. They'd collapse to a single vector, as they say, failing to distinguish anything.
Ah, right.
So you also need the contrastive part. You need to push these positive pairs, the two crops from the same image, away from negative examples.
Which are?
Crops from totally different images. So it's constantly learning. These are similar, but they are dissimilar from those. This constant push and pull forces it to learn truly abstract relationships and features that distinguish concepts. In practice, it often looks like a classification task, identifying the correct positive pair among many negative candidates. It's a powerful learning game.
Okay, learning by contrasting similarities and differences makes a lot of sense. What about other kinds of games or puzzles? Are there other ways models learn through self-supervision?
Oh yes, that's another incredibly fruitful perspective. The idea is, if a computer can successfully solve some kind of manipulation task or puzzle involving the data, it must demonstrate some level of deeper understanding. For instance, scrambled text or jigsaw puzzles. You can take a sentence and literally scramble the word order, or take an image and cut it into squares, like a jigsaw puzzle, and shuffle them.
And the model has to put it back together.
Exactly. If the model can put the words back into a grammatically correct and meaningful order, or reassemble the image squares correctly, it shows it understands things like grammar, semantics, or visual concepts like, how faces are typically structured with eyes above the nose above the mouth. Our source even mentioned something interesting for text. Sometimes the order of words are less important than the bag of words that appear somehow, meaning the collection of words itself holds significant information, even if the precise sequence is messed up.
Fascinating. What else?
Then there are denoising and diffusion models. These are huge right now, especially for text-to-image generation like Stable Diffusion or Midjourney.
Right, those are everywhere. How do they work on this game principle?
The game here is pretty straightforward. You take a clean image, you deliberately add a lot of noise like static to it, and then you train the model specifically to remove that noise and recover the original clean image. This iterative process of gradually removing noise is what we call diffusion.
Okay.
Now think about it. If a model gets really good at denoising, it must have learned a lot about what realistic images should look like, right? It needs an internal model of clean data.
I see. So it learns the structure by learning to undo the damage.
Precisely. And eventually you can take this trained denoiser, give it pure noise as input, and guide it to denoise that random static into a completely new, coherent image that matches a text prompt.
Wow. Okay, that's clever. Any other games?
Another important one is compression, often implemented using things called autoencoders. Imagine playing a game where you have to take a huge amount of high-dimensional data, like the millions of pixel values in an image, and compress it down to just a handful of numbers in a bottleneck layer.
Squeezing the information.
Exactly, squeezing it. And then, from just those few numbers, you have to try and perfectly recreate the original image on the other side. To succeed at this game, the model has to learn to save only the most essential, important information in that compressed representation, discarding all the redundancy. It forces it to extract really meaningful features.
And one more. The sources mention JANs.
Right, generative adversarial networks, or JANs. This is probably the most literal game. It's framed as a competition, an adversarial setup. You have two models playing against each other. One is the generator, or artist model, which tries to create realistic data, say fake images of human faces. The other is the discriminator, or critic model, which tries to distinguish between the real images from the training set and the fake ones created by the generator.
So the artist tries to fool the critic.
Exactly. The generator learns and improves by constantly trying to produce fakes that are good enough to fool the discriminator. The discriminator, in turn, gets better at spotting fakes. It's analogous to a human artist improving their drawing by repeatedly getting feedback on whether their work looks realistic or not. JANs can produce stunning results, though they can sometimes be quite tricky and unstable to train effectively.
That's a really fascinating overview of these different self-supervised approaches: prediction, contrast, jigsaws, denoising, compression, adversarial games. So we've talked about models learning to understand data by embedding it into these numerical representations, often called representation learning. And we talked about models generating new data. Are these two capabilities, understanding and generating, totally separate things, or do they somehow intertwine?
That's a great question. While they represent slightly different goals, analyzing versus creating, many of the most powerful modern foundation models are actually quite good at both. The ideal, the sort of holy grail here, is what we call a shared embedding space.
Okay, what's that?
It's a conceptual, high-dimensional space where equivalent meaning, regardless of the modality it comes from, whether it's an image, a piece of text, some audio, maybe even video, maps to the very same numerical vectors, the same fingerprint.
Whoa! So if you had an image of a man, you could embed it into this shared space, get its vector, and then a language generator, which understands that same space, could look at that vector and generate the caption "face of a man."
Exactly.
Or, conversely, you could input the text, "a fluffy white dog running on grass," into the space, get its vector, and then an image generator could use that vector to create a corresponding picture.
That's precisely the idea. It acts like a universal translator between different kinds of data, all based on shared meaning.
That sounds incredibly powerful, like how our own brains work.
It's very much analogous to our own cognition, yes. When you see a dog, hear a dog bark, or read the word dog, all those different sensory inputs relate back to a single, generalized, abstract concept of dog in your brain. It would be incredibly inefficient, biologically speaking, if our brains maintained completely separate and unrelated embedding spaces for vision, hearing, and language. The shared space allows for powerful cross-modal understanding and reasoning.
And it's not just about linking sources or different data types like images and text. Our source material talks about how this idea of a shared space is extremely useful in business.
Yeah.
Can you give us an example of that? How does this play out commercially?
Certainly. Think about understanding a customer. You might have data on their grocery purchase habits, their website browsing history, maybe even their fashion preferences if they shop for clothes on the same platform. If you can embed all that diverse information into a shared space, you get a much deeper, more holistic understanding of who that consumer is fundamentally.
Ah, I see.
And based on that unified understanding captured in the shared embedding space, you could then, for example, generate highly relevant fashion recommendations based on their grocery habits, or vice versa. It enables powerful cross-selling and personalization based on a genuinely deep understanding that cuts across traditional data silos.
That's a very powerful vision for business intelligence. But then there's an even bolder claim that pops up in our sources. What if language itself is the universal embedding space? That seems to elevate language beyond just being another data modality, making it somehow primary.
It's a truly profound claim, isn't it? And it resonates deeply with how we as humans seem to operate. We already think in terms of language, largely. It often feels like our internal operating system for conscious thought. Our shared knowledge of language helps us standardize knowledge across individuals and cultures, learn new things incredibly efficiently just by being told or reading about them, and ensures a level of consistency in our understanding of the world. If AI can truly harness language at that fundamental level, maybe using it as the common ground, it potentially unlocks enormous capabilities.
Okay, so if these models have this sophisticated understanding and generation capability, especially with language, how does all this tie into the current buzz around autonomous agents? We hear about them automating complex, multi-step tasks.
Yeah, that's really where a lot of this culminates in practical application right now. Consider training a robot with the instruction, make me a sandwich.
Hmm,
The older approach might map that text prompt directly to some abstract numerical plan representations and then directly to motor control actions.
okay.
But what if, instead, we map the prompt to language? What if the robot's first step is to output its plan in text? Like, okay, I will go to the kitchen, then I will take bread from the pantry, then I will get ham and cheese from the fridge.
Why would that be better? Why add that text step instead of just having it execute the actions?
Because we, as humans, and crucially, the language models themselves, can read and verify that plan before execution. If the robot outputs a nonsensical plan like, okay, first, take butter from the fridge and a knife from the freezer. Then use the butter to put bread on the knife. I will then proceed to the restroom to find the bread.
Right, you'd stop it immediately.
Exactly. We immediately know that plan is flawed, dangerous, or just plain wrong. Language provides incredibly fast shortcuts for reasoning and error checking. We don't need the robot to learn by painful, potentially disastrous trial and error that, for instance, putting a knife into a human being is a bad idea.
Hmm.
The language model can flag that as inconsistent with its world knowledge.
So the revolution that models like ChatGPT brought this incredible ability to understand and generate human language isn't just for chatbots or writing assistants. It extends crucially into robotics, planning, and other complex domains because language understanding allows for this vital step of iterative verification and self-improvement of plans before things go wrong in the real world.
Precisely. An autonomous agent, in this modern sense, is often built around a large language model that's applied iteratively on its own outputs. It first analyzes the task and generates an initial plan or output. Then, critically, it analyzes that output, perhaps using the same LLM, to evaluate it, critique it, identify flaws, and generate corrections or refinements. It loops.
So it reflects on its own work.
Exactly. It adds this layer of retrospection or self-correction, which makes the whole process much smarter, more robust, and more aligned with the original goal.
And our sources mention these agents can use tools. What kind of tools are we talking about here? Not physical tools necessarily.
Not necessarily physical ones, no. We're usually talking about tools that can be described and invoked using language. Think APIs, basically. Common examples include tools for performing internet searches, using a calculator for precise math, running code in a sandbox, accessing specific databases, or even invoking other foundation models that might be specialized in certain tasks, like image generation or data analysis. The central large language model acts as a kind of intelligent connector or orchestrator across these different specialized brains or capabilities.
That's a brilliant way to put it, a connector across different brains. So let's take an example. If I ask an agent to create a simple website showcasing two different breeds of dogs with pictures and short descriptions for each, how would that work with planning and tools?
Okay, so the agent, likely powered by an LLM, would first break that down into a high-level plan, probably expressed in language or structured text, something like 1. Search the web for information on two distinct dog breeds. 2. Find suitable images for each breed using a search tool. 3. Write short descriptions for each breed based on the information found. 4. Generate HTML CSS code for a simple web page structure. 5. Insert the descriptions and image URLs into the code. 6. Review the generated code and web page for correctness and completeness.
Right, a step-by-step plan.
Then, it would start executing that plan step by step. It would invoke the web search tool maybe multiple times. It might use the LLM itself to summarize the found information into descriptions. It would generate the code. And crucially, at each step, or at the end, it would likely use the LLM again to review its own work. Check the code for bugs, make sure the descriptions are accurate, ensure the images load, etc. It's this iterative process of planning, acting, using tools, and reviewing that makes it autonomous.
It's a self-correcting loop driven by language understanding. That's really powerful.
And what's becoming increasingly clear from all this work, cross-language, vision, planning, is that intelligence seems to be highly synergistic. When we try too hard to split intelligence apart into completely isolated, specialized tasks or separate brains, it often seems to lose crucial capabilities. The components become less effective than the integrated whole. Solving more problems, integrating more modalities and capabilities often makes the entire system smarter and improves performance across the board, sometimes in surprising ways.
So it's kind of like our own brain having one central, highly interconnected processing unit that integrates everything from vision to language to motor control, rather than having separate, isolated mini brains in each fingertip or handling just one sense.
Precisely that analogy. And it suggests that the AI market, particularly at the level of these large foundational models, might inherently be a winner-takes-all, or at least winner-takes-most market. You probably won't see the long-term success of completely separate, specialized large brains for just language, just vision, or just music operating in isolation. Instead, the most powerful systems will likely find ways to connect and leverage insights across all these domains for optimal performance. The synergy is too valuable. And this applies to business intelligence too, going back to that example. Understanding consumer behavior, recommending products, optimizing supply chains, these tasks are deeply synergistic. The ultimate goal is likely to leverage data and knowledge from all relevant disciplines and modalities into one single, huge, interconnected brain for the enterprise.
This vision of increasingly powerful, synergistic, centralized AI, it sounds incredibly potent, with immense potential to solve major global challenges. But as our sources hint, it also carries some pretty profound implications for how intelligence, and therefore power, might be structured in the world, doesn't it?
Indeed, it does. It clearly signals a potential for profound centralization of cognitive power and, by extension, economic and societal influence, possibly in the hands of a few key stakeholders who develop and control these dominant foundation models. If, hypothetically, everyone on Earth eventually relies on the same underlying large language model as a foundational layer for information access, communication, and decision-making, that creates a significant point of fragility.
How so?
Well, if that single core model is off, biased, or manipulated, then its flaws become systemic, affecting everyone who relies on it. There's less diversity of thought. But at the same time, the potential upside is also tremendous. This kind of concentrated intelligence really could unlock solutions to problems in medicine, climate science, materials discovery that are currently beyond our grasp. It could benefit humanity greatly if it's developed and deployed responsibly, ethically, and smartly. It's a double-edged sword, really.
Wow. Okay, that was a truly deep dive. We've gone from the limitations of early AI through the breakthrough of self-supervision, the power of language modeling, contrastive learning, diffusion, all the way to autonomous agents and the potential centralization of intelligence. It's amazing how these core ideas, understanding context, predicting sequences, finding similarities and differences, have led to such incredibly powerful systems.
It really is fascinating, isn't it? How these seemingly simple principles, like just predicting the next word or learning to denoise an image, when you apply them at a massive scale with enormous data and compute, they unlock these truly emergent abilities. The idea that simply scaling up next token prediction could lead to something exhibiting general intelligence, capable of planning, reasoning, and using tools is still mind-boggling. Even for people working deep in the field, it wasn't necessarily the expected path.
So, building on everything we've discussed, here's a final thought for you, our listener, to perhaps mull over. If meaning, as we explored, is fundamentally defined by the company it keeps, by its relationships and context, and if intelligence itself seems to be becoming increasingly synergistic and interconnected through these models, what new connections, what new companies, what previously unseen relationships might AI discover, not just between data points, but about our world, our societies, maybe even about ourselves that we haven't even begun to imagine yet? Thanks for diving deep with us.